Hi guys, this is Chevin Academy. Welcome to this channel. In this video, we are going to be looking at the design of Slab with a worked example. I've already created a video on introduction where we discuss the definition of Slab, its types, and also some design criteria that you have to consider in order for you to design a Slab. If you've not watched that video, you can check the description of this video in order to check the introduction part, because that will lay a background for you to be able to understand this particular one. So in order for this design to be practical, we are going to be using a simple layout of buildings with series of panels, about 8 panels, in which 2 are identicals. So we have the maximum panel size is 4.48 by 5 meters, while the minimum panel size is panel 4, which has a size of 4.43 by 5 meters. So based on this layout, it can be understood that this panel, from panel 1 to 4, they are all two-way slab, and as well as the flat slab is supported by drop panels, and we also have column heads. So when we cut a section across grid line B on the plan view, so we are going to be having this. So some of the things that we can detect from here is that our slab thickness is 175 based on this dimension. You know, in our previous video, I've explained that the minimum flat slab thickness according to BSA 1210 is 125. Then we also have the drop panel. So this flat slab is having both drop panels and column heads. You can see that the drop panel's thickness is 100 millimeters. The thickness of the flat slab itself is 175, and then the size of the column head is 900. In the total length of the column head is 900. So based on the explanation we made, for us to be able to determine the actual size of the column head, especially when you are having a flare column head, which is example of what we have here, that means you are going to offset 40 mm from the base of the drop panel, and then that will now be the dimension of the actual column head. So from here, the actual column head is 810 millimeters. So the drop panel has a size of 1.8 by 1.8, and also the column head type is a flare. That's a flare in the sense that when you look at the column head from the plan view, you are going to be seeing a circular cross section. And then the column head diameter, the overall diameter is 900. So the first thing we are going to be doing is we want to estimate the load. So we are going to be starting with the dead load. So, and then the dead loads for the slab includes the slab itself as well as the drop panel. Now, I told you in the previous section that the column head is not actually attached to the slab. It is attached to the column itself. So it is when you want to analyze the column that you include the weight of the column head. For this purpose, the dead load includes the self-weight of the slab, in which the slab has a thickness of 0.175. Then you multiply by the size of the panel. So for the purpose of this video, we are going to be looking at panel 3, that is the panel between grid line 3 and 4. So this is the panel we are going to be designing for this example. So, but for the other panels, the analysis is almost the same. Where there is 1 or 2 differences, I'm going to be pointing out those differences as we go along with this explanation. So the self-weight is calculated in kilonewton. That is, you multiply the thickness of the flat slab by the size of the panel. In this case, you are using panel 3, that is 4.48 by 5 meters, times the density of concrete, which is 24. So computing this, you have 101.64 kilonewton. Then you also calculate the self-weight of the drop panel. The thickness of the panel is 0.1, and then the size is 1.8 by 1.8. You multiply by density of 24, then you have 5.4 kilonewton. So then, but you can also add additional load such as partitions and finishes. So for the purpose of this example, we are just going to assume a partition and finish load of 10 kilonewton. So up next, we go to the total load. The total load is just the summation of the self-weight of the slab, the drop panel, as well as the partition and finish load. Then to now calculate for the life load is actually given in the code. It depends on the purpose of use. So for this example, we are going to be assuming a life load of 4 kilonewton per meter square. Based on what we know, flat slab is actually used to support a longer span as well as medium life load, especially if the life load is no more than 5 kilonewton per meter square. So we are going to be assuming a life load of 4, and then you multiply it by the size of the panel in order for us to get the load in kilonewton. The reason why we are trying to estimate this load in kilonewton is because in order for us to analyze this flat slab manually, we are going to be using some of the tables given in the British standard. So in order for you to estimate, to use those tables, you need to calculate your load in kilonewton instead of the normal kilonewton per meter square that we used to use. So once we've established the dead load and the life load, we can now determine the design load using the ultimate combination, that is 1.4 dead load 117.04 plus 1.6 life load of 96.8. So at the end of the day, you are going to end up with the total load of a design load of 318.74 kilonewton. So this is the total load that you are going to be having on each of the panel. That is for one panel, that is for panel 3 that we are taking as an example, the total load is 318.74. So, but you might want to convert this load to an area load, an area form. So in order for us to do that, all you have to do is to divide the total load by the area of the panel. The panel is 4.84 by 5. So you have a design load of 13.2 kilonewton per meter square, and also a design load of 318.74 kilonewton. So this is in kilonewton, and then the other one is in kilonewton per meter square. So both of them are going to be useful in this analysis. So before we proceed, if this is your first time on this channel, you can kindly hit the subscribe button if you want to see more technical videos on civil engineering design like this. Once you subscribe, you can also join our membership program by clicking on the join button next to the subscribe button down there. So once you click on it, you join the membership. We are going to be getting premium services like membership videos, where we are going to be diving more in depth on analysis and design. Then you're also going to be getting more, you'll be having more attention when we start making our live videos. So all your questions and comments will easily be answered once you join our members. And then as a member, you can also request us to make 1 or 2 videos on 1 or 2 topics. So this might be interesting for you. So you might try to join our membership program and also subscribe to this channel if you've not. So once we've able to estimate the load, the next thing is to move to the second step. So in order for us to, the second step is to determine the effective span. So looking at the cross section that we have here, the section we had here, you see that the center to center dimension of panel 3 is 4.48 between grid line 3 and grid line 4. But due to the inclusion of drop panels, this is going to affect the actual span, that is the effective span of the flat slab. So because of this, we need to determine the effective span. So the effective span can be calculated using this formula. The effective diameter of the column head, we first of all need to determine that in order to calculate the effective span, because the column head we affect and the drop panels we affect the actual span. So this is given by LC plus 2 into D minus 40. LC here is the size of the column in the direction in which we cut. So but let's say for example your column is 450 by 230. So if you are designing along the X direction where your column is 450, in that case your LC is going to be 450. If you are now designing along the Y direction where your column is 230, in that case your LC is going to be 230. So it depends on the section in which you are designing. So you are supposed to design along the X as well as along the Y. But for this video, we are trying to design it along the X direction. So that means our LC is going to be 230 because our column is 230 by 225 by 225. So DH is the depth of the column head. So based on this dimension, you can see that from the base of the slab to the bottom of the column head is 400 based on this geometry. So therefore, in order for us to get the depth of the column head, you subtract the thickness of the drop panel, which is 100. So that means your DH is given as 300. So if you substitute all that, LC of 225, DH of 300, so you are going to end up with a effective diameter of your column head to be 745 millimeters. So based on the code, the effective diameter is given as the lesser between this calculated value and the actual dimension measured. Because this column head is a flare type, so that means for us to determine the actual dimension, as I've explained earlier, you are going to offset 40 mm and then measured from ear to ear. So at the end of the day, you are, instead of 900 as your diameter of column head, you have 810. So the lesser between these two is going to be the effective diameter of the column head. So at the end of the day, we have an effective diameter of 745 millimeters. So once you've able to establish the effective diameter of the column head, you can now determine the effective span of the flat slab. So the effective span of the flat slab is just equals to this actual span of the flat slab minus 2/3 of the effective diameter. So if you compute that, you are going to have 4343.4 millimeters. So that means we are done with step 2. So the next thing we have to do is now to divide our panels into column strip and middle strip. So like I've mentioned in the previous video, in order for us to divide the panel into column strip and middle strip, you need to understand one or two things. So, and one of it is the size of your drop panel. So like I've mentioned, if your drop panel is, if the size of your drop panel is less than LX/3, then you have to ignore the drop panel. But if it is not, then you have to use your drop panel as a column strip. So the first thing we need to establish is that, and then in order for us to understand this division, you can see that from the, if you are using your drop panel, from the start of the drop panel to another drop panel is the middle strip. And then this column, this size here, since you are using your drop panel as your column strip, so the remaining part is the middle strip. So this diagram here is trying to explain the area that is considered as middle strip and the area that is considered as column strip. So as mentioned, the column strip is the maximum of LX/3 and your drop panel. So from here, since we are designing panel 3, our LX is 4.48. So if you calculate 4.48/3, you are going to have 1.6, which is less than the drop, because the size of the drop is 1.8 by 1.8. So because of that, we are going to use our drop as our column strip. So you can see this diagram. So this diagram here is trying to explain the division of the slab into column strip and middle strip. So wherever you have your drop panel, you connect them together to form the column strip, both in the X and the Y direction. Then the remaining part in the middle is your middle strip. So this is just the division. But in case if your drop panel is less than the LX/3, then you have to ignore it, and then you now calculate your actual drop column strip by dividing your LX/2. You divide it by 2. That is now going to be the total width of your drop panel. So now that we've established that the drop panel is 1.8, so definitely our column strip is going to have a total width of 1.8 since it is less than LX/3. So definitely the size of our middle strip is going to be the total length of our LX minus 1.8 along the X direction. But along the Y direction is going to be 5 meter minus 1.8. But because we only want to design along the LX, so we are just going to pick that. So then we also need to establish that our panel 3 is an interior panel. Interior panel in the sense that when you cut a strip, when you cut a section along X direction, you can see that the panel 3 is between grid line 3 and 4, which is at the middle, because we have a span to the left, we have a slab to the left, and we also have another slab to the right. So therefore it is being classified as an interior panel, or you can call it an interior span. So once we've been able to divide our flat slab into divisions of column strip and middle strip, the next thing we have to do is now to estimate the loadings. So in order to analyze it, we are going to be using these two tables, which can actually be found in BSA 1210, plus 3.7 under flat slab, and also plus 3.5 and 3.6. So the first thing you have to understand in the first table is you can see that you can calculate your moment and your shear force based on this coefficient. And then you also have each of these coefficients, the moment and shear force are in terms of F and L. L is the total load that we calculated in kilonewton, while L is the effective span of the panel. So since our panel is an interior panel, so definitely in order to calculate the moment, we are going to be using this side where we have interior span. For the interior span, interior panel is divided into span and support. We have the span region, we have the support region. So the span region is the middle strip, the support region is considered as the column strip. So because of that, the interior span, in order to compute the moment, we are going to be using 0.071 FL. And then for the interior support, that is the support of the slab, where we have the column strip, we are going to have in minus 0.055 FL to compute the moment. So this might be a little bit confusing, but whatever moment you get from here is going to be the total moment that you are supposed to distribute within the column strip and the middle strip. So, and then the second table, which is table 3.18, is explaining how you are going to separate or how you are going to distribute or share the moment you calculated using the first table between the column strip and the middle strip. So in summary, this table is saying if you have for a negative moment, that is for the organ moment, the column strip is going to take 75%, as we all know, because the negative moment is going to be acting at the support, which is the column strip. So that means it's taking 75%, and then the middle strip is taking 25%. But when you have a positive moment, that is a sagging moment, the column strip is going to be taking 55%, the middle strip is going to be taking 45%. We are going to be seeing how we are going to apply this practically. So in order to estimate the bending moment, we are going to be taking the positive moment first. So the positive moment is given by this formula, which was extracted from this table, 0.071 FL. So if you substitute F and L, which was already calculated from the effective span and also from the design load, you are going to have 98.3 kilonewton meters as your positive moment. So once we determine the positive moment, we now need to divide this moment into column strip and middle strip. So for the column strip, for the middle strip, positive moment for the middle strip, which is going to take from this table, is going to take 45%. So that means 45% of the span of the middle strip. What is the span of the middle strip, which was calculated earlier? So this 3.48 is the actual span of the panel minus the column strip. So this is supposed to be 3.04 because 4.48 minus 1.8 supposed to give us 3.04. So this is a typographical error. So then you divide it, the size of your middle strip, you divide it by the actual span divided by 2. So then you multiply it by the moment, the total positive moment. So that means you are going to have 56.3 kilonewton meter for the middle strip. So in order for us to calculate the portion of the column strip, is just going to be this factor here. You can do it the same way by saying 55% by this other size But instead of that, you can just say 1 minus this factor of 0.57, because the total of this is going to give us 0.573. So 1 minus 0.573 multiplied by moment, the total design moment, is going to give us 41.97 kilonewton meters for the portion of the positive moment that is going to be attributed to the column strip. I hope this is clear. So we now move to the negative moment. For the negative moment, since it's an interior support, so the negative moment acts as the support, so we are going to be using 0.055 FL. So just the same way, substituting your terms. So F is 318.74, L is 4.343, so you are going to head up with 76.14 kilonewton meters. So this moment is now divided between the column strip and the middle strip, and based on this table, for the column strip is 75%, for the middle strip is 25%. So if we do for the middle strip first, negative moment for the middle strip, 25% of the span of the middle strip, 3.04, divided by 4.84 divided by 2 multiplied by the moment, you are going to end up with 0.318 times the moment, which is 24.21 kilonewton meters, as the portion of the negative moment attributed to the middle strip. So we do the same thing for the column strip. We just do 1 minus this factor multiplied by this moment, and then we get the total moment for the column strip. So now we've been able to analyze the slab using the coefficient method, and then distribute this moment into column strip and middle strip based on the provision in table 3.18 of BS 8110, which explains the distribution of design moments in panels or flat slab. So if this is understood, the next thing is now to go to the provision of reinforcement, that is the design. But before we go to that, let me try to remind you, if you watch this video to this part, I will beg you to subscribe to this channel, because this is going to motivate and also assist this channel to grow. And then you can even buy us a gift by clicking on the get gifts. So we are going to be starting with the design for the middle strip first. So this is going to be the step 2. So for bending reinforcement, we are going to be establishing one or two things. We have to establish the B of our middle strip. So based on the calculation, the B of the middle strip is 3.04 meters. That is 3 meter 40 millimeters. Then we can now calculate the effective depth. You know, the middle strip, if you look at the division, the middle strip falls inside the slab. That is the middle of the flat slab itself. So that means the height of the flat slab in that region is 175. We assume a cover of 20, and then we are assuming we are providing reinforcement of 12 mm. So at the end of the day, you have effective depth of 143 millimeters. This is supposed to be in millimeters. 143 millimeters. So based on these two factors, we can now calculate our area of reinforcement. So the first thing we need to establish is the positive moment for the middle strip. This is from the previous slide, 56.3 kilonewton meters. So in order for us to calculate the area of reinforcement, we need to establish what is our K. And K is given by the formula M over BD square FCU. This is normal from BS 8110. So we can substitute all our values. For the moment 56.3, but you convert it to Newton millimeters. And then for B is 3040. Then D is 143 calculated. FCU is the strength of concrete. So for this example, we are assuming 25. So based on this, you are going to end up with a K value of 0.036. So from there, you can calculate your Z. So your Z is going to be 137 millimeters. I think all of this is understood right from the design of solid slab. So if you did not understand this, you can check my video on design of slab. I will also leave the link in the description of this video, or you can check the top right corner of this video right now. Once you get your Z, you can now calculate your area of reinforcement using this formula M over 0.95 Z Fy. Fy in this case is the strength of your reinforcement. So we are going to be assuming a high yield steel, which is what is common in practice, which have a strength of 410. So substituting all of that, that means your AS is, the moment is 56.3, your Z is 137, your Fy is 410. So at the end of the day, you are going to be having an area of 1055 millimeters. So that means you have to provide a reinforcement that's going to be slightly higher than this area. So at the end of the day, we say we provide 10 T12, that is 10 number of 12 millimeter reinforcement, which gives us an area of 1131, which is slightly higher than this. So because this is a slab, you can try to convert this area or this reinforcement in terms of spacing, if that is much more convenient for you. In order to do that, you just divide your B, which is what we have here, 30/40. You divide it by the number of bars to give you the spacing required. So that means at the end of the day, you are going to be having T12 at a spacing of 30/40 divided by 10. So that means approximately you are providing T12 at spacing of 300 for the middle strip positive moment. For the middle strip positive moment, you are providing T12 at a spacing of 300. So let's move to the negative moment for the middle strip. So the moment is 24.21 based on the previous slide. So we do the same thing. We calculate K. Then from there, just substituting for your B and D and FCU. From there, you get K equals 0.016156. Then you calculate your Z. From there, you calculate the area of reinforcement required, which is going to be 444 millimeter square. So you do the same thing. You provide reinforcement. So this is providing T12 at a 5 number of 12 mm reinforcement. This gives us an area of 565. So just the same way, you can calculate the reinforcement in terms of spacing. 30/40 divided by the number of bars, which is 5. So that means you are providing for the negative moment for the middle strip, you are providing T12 at a spacing of 600. But you know, according to the code, it is recommended that your maximum spacing is 300. So because of that, you can provide the same bar, 10 at a spacing of 10 number of T12, that is T12 as a spacing of 300. I hope that is clear. Based on the design, 12 mm bar at a spacing of 600 will work, but in order to avoid cracking and all of that, so you can provide T12 at 300. I hope that is understood. So the next thing is to move to the design for the column strip. So for the column strip, we are just going to do the same thing. So, but in this case, the column strip has a width of 1.8 meters. The column strip, that is the B. And then in the column region, this is specifically for the negative moments in the column strip. For the negative moment in the column strip, your D is 175. That is the height of the strip. You know, the height of the strip is going to be the height of the slab itself, 175, plus the thickness of your drop panel, which is 100. So at the end of the day, you have 275 as the depth of your effective depth, as the depth of your slab along the column strip for the negative moment. Underline that for the negative moment. Then minus the cover 20 minus the diameter of bar, we are assuming 12 because that is what we use. So that means we have an effective depth of 243. So let's work with the positive moment first. Based on our calculation, the positive moment is 41.97 kilonewton meters. So because of that, we calculate our K just like with the way we did earlier. But mind you, you see that here, the B that we use here is 3.04 meters, not 1.8. The reason for this is for the positive moment along the column strip is going to occur where the width is 1.3. For you to understand that, let me go back to where we have the column strip and try to explain this so that you get it better. So in order to explain what I mean, so let's say for example, you cut your section along here. If you cut your section along here, your bending moment is going to go this way. So this is actually where the positive moment is. This is where we have the negative moment. This is positive, this is negative. This is positive, this is negative. You can now see that the middle strip, the column strip along the y direction or along this direction is majorly on the negative. But if you cut your section close to where we have the drop panel, so that means you are going to be having something like this. So this is positive moment, this is negative moment. This is positive moment, this is negative moment. This is positive, this is negative. So this is what I'm trying to explain. You can see that this is the positive moment for the column strip. It is this region. You can see that the size is the same thing as the size of the middle strip, which is subtracting 4.484 from 1.8, which is the size of the drop panel. So that is why for the positive moment along the column strip, the width is going to be the same thing as the width of the middle strip. I hope that is clear. So let's continue with the explanation. So that explains the reason why we have for the column strip here, the positive moment, why we are using a B value of 3040 instead of 1.8, which is the size of the column strip. I hope that is clear. So after that, you calculate your K. From this value, from K you get your Z, 138.6. And then you can now calculate your area of reinforcement just like the way we did by substituting Z and Fy. At the end of the day, for the positive moment along the column strip, it requires an area of 77.4 millimeter square. So we are going to be providing the same thing, 10 number of bars with a size of 12 mm. So for the negative moment, and also if you notice closely, what we use for the D is also 143 instead of 243. This is because where we have the positive moment, that region has a thickness of the slab. There's no drop panel in that place. So that is why the D is 143 instead of 243. The only region where you are going to be using the D of 275, that is including the drop panel and the thickness of the slab, is the negative moment for the column strip. That is the only location where you use a D of a D comprises of the thickness of your slab and the drop panel. So because of that, you are going to see that here when we substitute for B, our B is now 1.8, which is the thickness of the column strip along the drop panel, and then the D is 243. So you calculate your K, then you calculate your lever arm. Then from there, you calculate the area of reinforcement required by substituting the value of your moment, the value of your lever arm, and the strength of reinforcement. So you are going to get 561 millimeter square. So you can also provide 6 number of 12 mm bar for the slab. So at the end of the day, our design summarized that along the column and middle strip for construction purpose, we can provide 10 mm of, but for the column strip in this region, you know the column strip is 1.8. So definitely, instead of you using the spacing, is now going to be, the spacing is going to be 1.8 divided by the number of bars. So it's not going to be, so you have 1.8 divided by the number of bars if you want to calculate the spacing, which is 6. So that means 6 number of 12 mm is equivalent to 12 diameter of bar at a spacing of 300 for this one. And then this one is also equivalent to 12 diameter of bar at a spacing of 300, because if you divide 10 by this b, 30, 40, so you are going to have 300, approximately 300. So that means along the column strip and the middle strip, you can use a reinforcement of 12 mm bar at a spacing of 300 for both column strip and middle strip based on this design. We've come to the end of this video, but the design of flat slab does not actually end here. For you to now finalize this design and check if what you provided for the depth of your column strip, for the depth of your drop panel, and then if the thickness of your slab is adequate, you now need to check for punching shear. So we are not going to be covering that in this video. We are going to have another video where we talk about the punching shear checks for flat slab, and this is going to be specifically for people that join the membership program of this channel. So if you want to watch the video on checking for punching shear based on this design, based on the design that we are doing here in this video, you can join our membership program, and from there you'll be able to see the video on how you check for punching shear, just like a continuation to this design. In this section of the video, you're able to understand how to analyze a flat slab, how to determine the moment, and also distribute this moment into column strip and middle strip, and then how to provide the reinforcement for both column strip and middle strip for the positive moment and also for the negative moment. Thank you. I hope you've learned one or two things. Don't forget to subscribe. See you in the next one.